Okay, so let's take a look at the questions on page 390 that were your homework. In the first one, it just wants the speed of sound at each of the temperatures. So it gives you the temperature. So for A, it's minus 15 degrees Celsius. So it's going to be your equation, 331 meters per second, 0.59 times the temperature. So 0.59 meters per second degrees Celsius. And the first temperature is negative 15 degrees Celsius. So the degrees Celsius is going to cancel. 0.59 times negative 15 is negative 8.85. And when you take that away from 331, you should get 322.15 meters per second. The second one, exactly the same idea. 331 meters per second times plus 0.59 times the temperature. And this time the temperature is positive 15 degrees. So it's going to be 8.85 again when you multiply those two together. And so this time when you add it, you get 339.85. 339.85 meters per second. Should be easy enough. The third one, the temperature is 25 degrees. So 331 meters per second plus 0.59 meters per second degrees Celsius times 25 degrees Celsius. So 0.59 times 25 is 14.75. When we add that to 331, you get 345.75 meters per second. All right. And the last one in part A is with 33 degrees. So 331 meters per second, 0.59 meters per second degrees Celsius times 33 degrees Celsius. So 33 times 0.59 is 19.47. And so when we add that to 331, you get 350.47 meters per second. So number one, finished. Number two, a little different spin. This time they're telling you the speed and they're asking you to solve for temperature. So you need to rearrange it. So you want to get the temperature alone. So it'll be V minus 331 meters per second. And that's going to equal 0.59 meters per second degrees Celsius T. And now to get the T alone, divide by the 0.59. So T will equal V minus 331 meters per second divided by 0.59 meters per second degrees Celsius. So for part A, it's 352. So 352 meters per second minus 331 meters per second divided by 0.59 meters per second degrees Celsius. And when you do all that, you should get, running at a space, 35.59 degrees Celsius. Exactly the same thing for this one. So if we use what we just rearranged for, so it'll be T equals V minus 331 meters per second over 0.59 meters per second degrees Celsius. It becomes T is equal to, so for B it's 338. So 338 minus 331, so that's about 7, divided by the 0.59 meters per second degrees Celsius. And so when you do this, you get 11.864 degrees Celsius. Next one's 334. So again, V minus 331 meters per second, and then divide it by the 0.59 meters per second degrees Celsius. So it becomes 334 minus 331. And then divide by 0.59. So 3 on the top divided by 0.59, 5.085 degrees Celsius. And the last one, again, V minus 331 divided by 0.59. That's going to be T. So what was the speed? 319. So this time it's going to be a negative. 319 meters per second minus 331 meters per second. So that's going to be negative 12 over 0.59 meters per second degrees Celsius. And when you do the math, you get negative 20. Negative 20.34 degrees Celsius. Okay? So hopefully you got a hang on that equation. Hopefully you know it now. So let's move to question number 3. Question number 3 says, a ship's horn blasts through the fog. The sound of the echo from an iceberg is heard if only I could see what that number is, 3.8 seconds later. So here's the ship. The sound goes out, hits the iceberg, and comes back. And the full time is 3.8 seconds. Okay, and the question says the temperature is negative 12 degrees Celsius. And it wants to know how far away is the iceberg. So the first thing you're going to do is figure out what's the speed with that negative 12. So 331 meters per second, 0.59 meters per second degrees Celsius, times negative 12 degrees Celsius. And so you will get a speed of 323.92. 323.92 meters per second. So now you have a speed and you have the time and you want the distance. So you can do VAV equals delta D over delta T, rearrange for delta D. So delta D equals VAV times delta T. So you have your 323.92 meters per second. And then you need to make a decision about the time. The time is over and back. So your options are either divide the time by 2 now or divide the distance by 2 later. So if you use the full time, 3.8 seconds, you will get a delta D of 1,230.896 meters. But that's over and back, so that's the total. So one way would just be half of that. So it would be 615.448 meters. That's how far away the iceberg is. There's a part B to this question, which asks, how might weather conditions affect the accuracy of the answer? Well, really, there's two ways. One way is it might not be a uniform negative 12 degrees the whole way along. It might get colder when it gets to the iceberg. And the second part is the question said it was foggy. And so foggy means there's more moisture in the air, more air particles and water particles in the air, so it might be denser, and so therefore it might travel quicker. Okay, so that's number 3. Number 4, an electronic fish finder uses sound pulses to locate schools of fish by echolation. What would be the time delay between the emission of a sound pulse and the reception of the echo if the school of fish was located at a depth of 35 meters in a lake? Assume the temperature is 20 degrees. All right, so we have 35 meters, and it wants to know the time delay. So it means down and back. Okay, so this 35 meters is just one way, but really we want the delta D total to be 70 meters, and we're looking for delta T total. Okay, so we're going to use VAV is equal to delta D over delta T. So delta T is equal to delta D over VAV. So we know our delta D is 70 meters. Now the question is, what is our V? Do we use 331 plus 0.59 times the temperature? Well, the problem with that is that's for air. And I'm not sure about you, but I haven't seen that many fishes that actually go around in a lake swimming in air. So you have to go back to that chart that I showed you the other day, yesterday, on page 387. And it says that it is a lake. So a lake is fresh water. So if you look on the chart on page 387.